Okay. So we know that momentum is the quantity of motion that an object possesses. Now, if that's true, then it should be very easy to calculate momentum. It should be the mass of the object in kilograms multiplied by the velocity of the object. So we have to pay attention to the sign, and it needs to be in meters per second. The symbol for momentum is the lowercase p, and I do not know why. The units would be kilogram meters per second. Now, this really comes from Newton's second law, F is equal to ma. And we know if we apply a force, we're going to cause the object to accelerate. So we can say that F is equal to m delta v over delta t. Or we can rewrite that as F delta t, a force applied over a period of time, is going to cause a change in momentum. Is everybody okay with that? So a force applied over a period of time, that's going to be in newtons times seconds. And a newton times a second must then equal kilogram meters per second. And if you play with the units, you can easily see it does, because kilogram meter per second squared multiplied by a second is definitely going to give me kilogram meters per second. Okay, you must pay attention to the sign of the velocity. It is very easy when they're headed toward each other like that to forget to make one positive and one negative. So be careful. That's just a real common, mistake that folks make, including your teacher. All right. So I'm going to pause that. So we can talk about conservation of momentum. During any collision, all right, let me make sure I tell you that correctly. And I want it to occur. Okay, when you spell occurring, is that a double R? Did I do that right? Yes? No? It is, right? I think it is. Occurring in an isolated system. And we'll define an isolated system in just a second. Momentum before the collision must equal momentum after the collision. Okay, now you need to know what an isolated system is. Well, an isolated system is defined to be a system in which the vector sum of all external forces acting on the isolated system must be 0. Okay. So if we are dealing with an isolated system, which is what you're always going to have, we're going to say the momentum before the collision, so P initial, has to equal P final. And you can deal with as many bodies as you want. Typically it's just two, so you say M1V1 plus M2V2 equals M1V1 prime plus M2V2 prime. M1, M2, masses of objects 1 and 2 in kilograms. V1, comma V2 are the velocities. I was going to say speed, but that's not true. Velocities of objects 1 and 2 before the collision. And oftentimes one or both of those will be 0. Think about when you shoot a gun. What's the speed of the bullet before the gun is shot? 0. What is the speed of the gun itself before it's shot? 0. That rests on your shoulder. So that sets us up for recoil, which is a special case of momentum, very easy to deal with. V1 prime and V2 prime are the velocities of objects 1 and 2 after the collision. Okay, stop there. Okay, if we want to deal with collisions in one dimension, all on the y or all on the x-axis, then our equation is simply going to be that little rascal right there. Okay? If, however, we deal with collisions in 2 dimensions, which of course on the AP they will do that, you must separate it into motion along the x-axis and then motion along the y-axis. So you'll have M1 V1 x plus M2 V2 x equals M1 V1 prime x plus M2 V2 prime x. And then they'll give you something going on the y-axis. And typically what you'll do is use one to help you solve another. So everything looks exactly the same except for this little subscript, it becomes a y. And what typically happens is this quantity over here is 0 so that you can get V1 y prime in terms of V2 y prime or some variable there, and you can go back and solve it, plug that into your x-axis. And I'll do one of those with you because they're a little bit more fun algebraically. And we need to talk about ballistic pendulums, so I will do one of those with you next time we meet. And then the last part of it, section 7.4, talks about collisions in 2 dimensions, which is what we're going to do right there. And then the very last thing is the center of mass. And basically what you're doing there is you're looking for, let's say you have some shape that's kind of a funky shape like that. Where could you support that object so that it would completely balance? Because that point is called the center of mass. And we'll do a little activity with that that's real simple, but I think it drives home the point pretty easily. Because what you've got to do is what we're going to do in the activity is we're going to take a plumb bob and hang it. And then we're going to punch another hole over here and turn it, let it hang, and where these 2 points intersect is your center of mass. And you should be able to put your fingertip there and then balance that cardboard shape. Did y'all do that in Miss C's room or Mr. Laga's room last year? Anybody remember? No? Okay. Well, I'll pull that out. It's just a real quick 5-10 minute activity, but it makes it a little bit easier to understand center of mass. And we'll play with the center of mass. There's only 5 parts of this chapter, but some of them are a little bit more intense than others. The ballistic pendulum we want to spend a little time on, and then the 2-dimensional collisions we'll spend some time on those. So I think I've kind of filled your head enough for today, so we're going to stop right there.